Welcome to session 2 in lesson 1. In this session you will learn the basic principles of the arbitrage pricing theory and multi-factor models of risk and returns. The learning goals for session 1.2 are: you should be able to apply the concept of multi-factor models of risk and return. You know the concept of arbitrage pricing theory, and students should be able to know the differences between the APT and the CAPM. The single factor model. We begin with a familiar single factor model. Uncertainty in asset returns have two sources: a common or macroeconomic factor and a firm-specific event. By constructing, the common factor has zero expected value because it measures new information concerning the macroeconomy. New information implies a revision to current expectation, and if initial expectations are rational, then such a revision should average out to zero. The single factor model. Formally, the single factor model of excess returns is described by the formula below, where the expected excess return plus the beta times the factor plus the firm-specific disturbance equals the excess returns. Notice that if the macro factor has a value of 0 in any particular period, meaning no macros surprises, the excess return on the security will equal its previously expected value plus the effect of firm-specific events only. The non-systematic components of returns, the EIs, are assumed to be uncorrelated across stocks and with the factor F. Multi-factor models. The factor model's decomposition of returns into systematic and firm-specific components is compelling, but confining systematic risk to a single factor is not. It stands to reason that a more explicit representation of systematic risk, allowing different stocks to exhibit different sensitivities to its various components, would constitute a useful refinement of the single factor model. It is easy to see that the models that allow for several factors, multi-factor models, can provide better description of security returns. Suppose the two most important macroeconomic sources of risks are uncertainties surrounding the state of the business cycle measured by unanticipated GDP growth and changes in interest rates. The multi-factor model equation. The return on any stock will respond both to sources of macro risk and to its own firm-specific influences. We can write a two-factor model describing the excess return on stock I in some time period as follows. It's the expected excess return on stock I plus the sensitivity of that stock to the GDP factor plus the sensitivity of that stock to the factor of interest plus the firm-specific influences. The two macro factors GDP and interest rates comprise the systematic factors in the economy. As in the single factor model, both of these macro factors have zero expectations. The coefficient of each factor in the formula measures the sensitivity of share returns to that factor. For this reason, the coefficients are sometimes called factor loadings or equivalently factor betas. Arbitrage pricing theory. Stephen Ross developed the arbitrage pricing theory (APT) in 1976. Like the CAPM, The APT predicts a security market line linking expected returns to risk, but the path it takes to the security market line is quite different. The APT relies on three key propositions. First, security returns can be described by a factor model. Second, there are sufficient securities to diversify away idiosyncratic risk. And third, well-functioning security markets do not allow for the persistence of arbitrage opportunities. Continuing on the arbitrage pricing theory, an arbitrage opportunity arises when an investor can earn riskless profits without making a net investment. For example, suppose IBM trades at $163 on Nasdaq and on 165 on the New York Stock Exchange. Therefore, you could buy the shares on Nasdaq and simultaneously sell them on the New York Stock Exchange, clearing a riskless profit of $2 per share without tying up any of your own capital. Continuing on the arbitrage pricing theory, an arbitrage opportunity arises when an investor can earn riskless profits without making a net investment. For example, suppose IBM trades at $163 on the Nasdaq and on $165 on the New York Stock Exchange. Therefore, you could buy the shares on the Nasdaq and simultaneously sell them on the New York Stock Exchange, clearing a riskless profit of $2 per share without tying up any of your capital would result. The law of one price states that if two assets are equivalent in all economically relevant respects, then they should have the same market price. The law of one price is enforced by arbitrageurs. If they observe a violation of the law, they will engage in arbitrage activity, meaning simultaneously buying assets where it is cheap and selling where it is expensive. In the process, they will bid up the price where it is low and force it down where it is high, until the arbitrage opportunity is eliminated. Asset pricing theory and well-diversified portfolios. By now, we know that in a well-diversified portfolio, its firm-specific or non-factor risk becomes negligible, as the number of securities increases so that only the factor systematic risk remains. We can separate the variance of the portfolio into its systematic and non-systematic sources. Returns as a function of the systematic factor. Portfolio non-systematic risk will approach zero for any portfolio for which each weight becomes consistently smaller as the number gets larger. This property motivates us to define a well-diversified portfolio. Panel A plots the excess return of a well-diversified portfolio A with the expected excess premium equal to 10% and a beta equal to 1 for various realization of the systematic factor. The intersection with the y-axis, the systematic factor, is 0, implying no macro surprises. Panel B plots the excess return of a single stock. As it is undiversified, it is subject to non-systematic risk, which is seen in a scatter of points around the line. The well-diversified portfolio's return in panel A, in contrast, returns as a function of the systematic factor. Portfolio non-systematic risk will approach zero for any portfolio for which each weight becomes consistently smaller as the number gets larger. This property motivates us to define a well-diversified portfolio. Panel A plots the excess return of a well-diversified portfolio A with the excess return equal to 10% and the beta equal to 1 for various realization of the systematic factor. The intersection with the y-axis is where the systematic factor is 0 on the x-axis, implying no macro surprises. Panel B plots the excess return of a single stock. As this is undiversified, it's subject to non-systematic risk. This is seen in a scatter of points around the line. The well-diversified portfolio's return in panel A, in contrast, is determined completely by the systematic factor. Returns as a function of the systematic factor, an arbitrage opportunity. As previously shown, in a well-diversified portfolio, we are only left with systematic or factor risk. This is the basis of the security market line. The figure below shows two diversified portfolios, A and B, with betas of 1, but with differing expected rates of returns, for A equal 10% and for B equal 8%. Could portfolios A and B coexist with the return pattern depicted? Clearly not. No matter what the systematic factor turns out to be, portfolio A outperforms portfolio B, leading to an arbitrage opportunity. The outperformance is 2%. Market participants will benefit from the arbitrage opportunity by taking long and short positions, which will put pressure on security prices and force the return discrepancy between the two portfolios to disappear. We conclude that such arbitrage activity ensures that well-diversified portfolios with equal betas will have equal expected returns. An arbitrage opportunity. What about portfolios with different betas? Their risk premiums must be proportional to beta. Suppose that the risk-free rate is 4% and that a well-diversified portfolio C with a beta of 0.5 has an expected return of 6%. Portfolio C plots below the line from the risk-free asset to portfolio A. Consider, therefore, a new portfolio D composed of half of portfolio A and half of the risk-free rate. Portfolio D's beta will be 0.5 times 0 plus 0.5 times 1 equals 0.5. And the expected return is equal to 0.5 times the 4% of the risk-free rate plus 0.5 times the 10% of portfolio A, which is equal to 7%. Now portfolio D has an equal beta but a greater expected return than portfolio C. From our analysis in the previous paragraph, we know that this constitutes an arbitrage opportunity. We conclude, to preclude arbitrage opportunities, the expected return on all well-diversified portfolios must lie on the straight line from the risk-free asset. The no arbitrage equation of the arbitrage pricing theory. The previous graph was related to risk premiums on well-diversified portfolios to their betas against the macro factor. As a final step, we would like a security market line that relates the portfolio risk premium to its beta against a market index rather than an unspecified macro factor. This last step is easy to justify because all well-diversified portfolios are perfectly correlated with the macro factor. This means that betas measured against the market index are just as informative about relative levels of systematic risk as are betas measured against the macro factor. Therefore, we can write the non-arbitrage equation of the arbitrage pricing theory for any well-diversified portfolio as follows. The expected excess return on portfolio P is defined by the product of its beta and the risk premium of the market index. Comparing the arbitrage pricing theory versus the CAPM, we need to raise the questions. Is the APT as a model of risk and return superior or inferior to the CAPM, or do we need both models? The APT serves many of the same function as the CAPM. It gives us a benchmark for rates of returns that can be used in capital budgeting, security valuation, or investment performance evaluation. Moreover, the APT highlights the crucial distinction between non-diversifiable, so-called factor risk, which requires a reward in the form of a risk premium, and the diversifiable risk, which does not. Moreover, the APT provides an expected return beta relationship using a well-diversified portfolio that can be constructed from a large number of securities. It does not rely on the elusive and impossible to observe market portfolio of all assets that underpins the CAPM. A well-diversified index portfolio can suffice for the APT. In spite of these apparent advantages of the APT, it does not fully dominate the CAPM. The CAPM provides a statement on the expected return beta relationship for all securities, whereas the APT implies that this relationship holds for all but perhaps only a small number of securities. The APT cannot rule out a violation of the expected return beta for any particular asset. For this, we need the CAPM assumptions and its mean variance dominance arguments. We are at the end of session 1.2. After having carefully studied the slides and relevant chapters in the book, please start with the review questions.